Gravity Basics Part 3. For a planet of radius r and uniform mass density d, derive expressions for little g as a function of r. First for r less than big R, and then for r greater than big R. Then we're going to draw a quick graph of our answers. What we have here is we have a planet, and it has a uniform mass density of d, and there's the center. And what we want to know is, we want to say, you know what? If we're only that far out, these are supposed to be circles, but oof. If we're only that far out, what's the value of little g? And the overall radius is big R right there. And then what happens if we have r where we're beyond the radius of the planet? How does the acceleration due to gravity change when we're inside the planet? And then when we get beyond the planet and keep going, what happens to the value of g? That's what we're after here in this problem. So the deal is, and I'll explain this in a minute, only the underneath mass is relevant. Exclamation point. So here's what we're going to do. We're going to take a pretend mass, little m, and I'm going to put him right there. So that's a pretend mass right there. We're going to say little g for little r is less than big R. So we're going to do that case first. We said in an earlier video that that should equal the force of gravity on any mass divided by the mass itself. Well, what's the force of gravity on this little mass right here? Isn't it equal to big G times the mass underneath? And I'm putting dots around that because those are the dots that I'm showing in this picture on the right. Big G times the mass underneath times little m divided by the distance apart that their centers of mass are, which is r squared. Well, that's just Fg. Now, you see I've got this little m in the denominator, so I need to divide that whole thing by m, which means that little g is going to equal big G times the mass underneath divided by little r squared. Now, what's the little mass underneath? Didn't you learn in chemistry that density is mass divided by volume? So that means that mass, right here, is density times volume. Well, what's the volume of this spherical dotted thing? Isn't it 4/3 pi little r cubed? That's what that mass is. Let's write out what we have here. G d 4/3 pi r cubed, and then I've got an r squared in the denominator. So how does this simplify? Two of those r's go away, and I think that's it. 4/3 pi g d r. Let me put a square box around that, square box around that. What if r becomes bigger than big R? Now we're above the planet and going away. We're going to use the same process here. We're going to say little g is always the force of gravity on m. So if you look at our picture now I've moved m like right there. See that in the upper right corner? There's where little m is now. The force of gravity on him is going to be big G. Now what's the mass underneath now? The mass underneath now is just the planet. See, it's the whole planet multiplied by m divided by the distance between them squared. But according to this equation, we have to take the gravitational force and we got to divide by little m. So little m's cancel again. So this leaves us with little g is equal to big G times the mass underneath divided by the distance away squared. Let me put that right there. Well, what's the mass underneath now? The mass underneath is just the mass of the planet, which is the density of the planet multiplied by the volume just of the planet, big R cubed, which means when we simplify this, it's going to come out to be what? 4/3 pi g d, don't forget the d, big R cubed, and then we've got an R squared in the denominator. So that 4/3 is a little bit offset there. That's what we've got. Now, if we graph that, what's that going to look like? You can see that when R is less than big R, G grows linearly with R. As we get away from the planet, it falls away 1/r squared. We're going to run into a lot of graphs like this when we get to electricity, but it's going to look something like this. Here, G is proportional to R. You can see that in the equation, top middle of the screen. Little g is directly proportional to R. As we get away, G is proportional to 1/little r squared. Again, that is shown in the equation right there.